we're going to be dealing with one variable statistics for now. Okay? So no dependent versus independent or dependent versus multi-independence at this point, just one variable statistics for now. So we're talking about measures of central tendency. What does that mean to anybody over here? When you read that, what does that mean to you? Okay. Is there more than one measure of central tendency? You actually know them all. You learned them in grade 5 or 6 or 7. Okay, we have mean or average. We have median, mode. I guess this is kind of redundant, but what are the purposes of each of these? What are their functions? What values? What do we care about them? What do they do for us?
They let us analyze the data.
They let us analyze it. They say, you may, the mean says, Milad, no, you may now analyze the data. Anybody else? Anybody else? Yeah.
Is median like the centermost value?
Yeah, well, you're talking about definitions first. Okay, you want to define first?
Yeah.
That's for odd number of data points. But for an even number of data points, it's the average of the two central data points. You guys understand? Now, do you understand what I mean by that? Why do you understand why I'm defining it twice? If you have three numbers, let's say the numbers are 5, 10, and 15, okay? What's the middle data point there, 5, 10, and 15? Well, 10, right? There's a single data point. But if you had 5, 10, 15, 20, you don't have a central data point because you have an even number, but you take the two middles, right? 10, 15, add them, divide by 2, which is the average of the two. Okay, what does it mean? Mean is average. What is average?
You add up all the numbers, divide the numbers of how many there are present.
Yep. And if I was to use sigma notation for that, well, I guess we'll get there in a second. Let's do definition of mode and then we'll go back. Definition of mode, yes sir?
The value that occurs more.
Yeah. The most frequently occurring data points? Okay. I don't think we have a mathematical symbol for median, so I think we simply write, median is 6 or 12 or whatever. And for mode as well, I think we just tend to write mode is good. But when it comes to average, we do use a nomenclature or notation, but we use a dual notation, okay? When it comes to average and measures of spread like standard deviation, which we'll discuss later, and variance, we kind of take our definitions, we break them along two parallel paths. And we should talk about why. But before we do that, what was my original question? What's the use of this stuff? Of anything? Do you care? Does it do anything for you? Yeah?
It helps you analyze the data.
Okay. Anybody want to take that further? Okay. Let it go then for now, yeah?
Like, if you know the mode, you will know the pattern of the data.
Oh, okay, we're starting to get somewhere a little bit better. Okay. It's about tendency. It's about being able to talk about the behavior of the data as a whole, to the best extent that you can. To the best extent that you can. Being able to talk about the behavior of a population of information, or a sample of a population of information. And these are good barometers for the tendency. of that behavior. So I'm going to break this off into two parts soon. But before I do, we should mention something else. Because we talk about a clump of data and the tendency of that data, or the general behavior of that data to the best that we can label it as having a general behavior. But then there's the term outlier. Anybody here to tell us what an outlier is? Yeah.
A value that is completely different from the rest.
I'll even define it. I would change this a bit. I would say value that significantly deviates from the central tendency to a much greater extent than others. Does that make sense? So let's say you're talking about the average. Say the average on a test is 75%. You know, a bunch of 75s and 70s and 80s, 85s, 86s, blah, blah, blah. You know, let's say you have a lot of 75s, for example. Let's say you have one failure. And then the next data point up from that is like a 60. Let's say there are a bunch of people in the 60s. We would talk about that data point as being an outlier. Now, can you necessarily omit an outlier? Yes or no? Why? Can you just throw it in the garbage? We've discussed this. Yeah.
Well, like for example, on lab, we didn't throw the outlier in the garbage because
So could you repeat that?
for example, in a lab, a scientific lab,
Yeah.
we wouldn't throw the outlier in the garbage because it does represent significance in when you analyze whatever results you've gotten.
I wouldn't say it like that. Anybody else want to pick up on why you can and can't throw away an outlier? Yeah.
Sometimes throwing away the outlier might create bias because it would shift the trend, perhaps.
Okay. Anybody else? I would say it again. I think you guys are saying it backwards. If the outlier is a result of the true nature of the system or the process, then that's part of the way the process behaves. You can't just throw it in the garbage. Okay? And if your intent is to understand the true nature of the process or system which you're analyzing, and you throw that away, then you're shooting yourself in the foot. Okay? If your objective is to, I don't know, show off, let's say you're a teacher and you're trying to show off with marks, and your objective is to show that you have a high class average, sure, then it serves your purpose. You get rid of that outlier because, look at my class average, it's wonderful, everybody does so well, right? Depends on your objective. But if we operate under the assumption in this course, which we pretty much do, because we're looking at things from a theoretical perspective, not from an agenda perspective. Our agenda is to learn this stuff properly. Then the idea is, yeah, I want to get an idea of what's really representative. I want to know what's really going on with my system. And if I just throw away an outlier, well, then I'm not getting a true representation of my system. But there are some situations where actually throwing the outlier away would give you a true representation of the system's behavior. Or to say that in another way, the occurrence of that particular value is not reflective of the true behavior of the system. And that might be for reasons like experimental error, right?
You accidentally push the button.
Accidentally push the button, sure. Let's say you're supposed to be analyzing the performance of a sprinter, their last 100 races. And on one of their races, you know for a fact, they had the flu. Okay? And you get a time that's ridiculously high. Is it reasonable to throw that time away? I think so. Because there are circumstances that you are aware of, okay, that totally threw off the data. Okay, so do you guys understand the difference? Just because something is an outlier doesn't mean you throw it in the garbage. On the contrary, it stays in there unless you have reason to believe it is not representative of reality. Now it's different if you're a CEO of a company and you're trying to show that you have an agenda. If you have an agenda, that's different. I'm not talking about an agenda. My agenda here is under the assumption that our objective is to really know what's going on. Okay? So now we're going to generate this split, and it'll go for mean. And it'll go for other stuff. And for things like mean, the difference is just going to be definitional, but when it comes to variance standard deviation, it's going to be more than definitional, it's going to be formulaic. So when we talk about mean or average, when we talk about average of a population, you talk about adding up all the data points. Let me just define it for population. You use the symbol mu. And if I was to write that in sigma notation, we have that. Okay. Questions on that? So when it comes to population, you simply add up all of the data points in the population, where there are capital N data points in the population, and you divide by the number of data points, and that gives you average, right? As you guys know. Sample of population, what does sample of population means? It means if there were 100 people in the population, or 100 data points rather in the population, you randomly grab 30, you're not dealing with all of them. Sorry, my contact lenses throwing me off. So they use a different symbol. Statisticians develop X with a bar over it, what they call X bar. And instead of using capital N, they use lowercase n to indicate, well, this is a subset of the total quantity of data points. And in sigma notation, the only difference is the capital N turns into a lowercase n.
Over.
Mm-hmm. Now, mathematically, if you take a look at those two, is there any difference in terms of the mathematical or the operational definition here, in terms of what you do? You know, here you add them all up, you divide by the total that you have. Add them all up, you divide by the total that you have. So there's no difference. So at this stage you might look at that and say, well, this is so stupid, because like if it's the same thing, why are you creating more nonsense like two different? And there'll be a reason for it later. Okay. So, are we clear on the sigma notation? This means start with that as a 1, replace that I with a 1, and this says add to that x1 the next one, which will be x subscript 2, and then add to that. We talked about how that's addition, how that's multiplication, but we're not doing that now. Okay? Let me just take a quick look here what we have next in the actual text, so that we're sort of in line with what the book is doing. We have to do weighted average as well. I'm assuming that's kind of up. Okay. Yeah, okay, let's talk about weighted average. Okay, can I erase over here? Can I erase over here? just from what you believe, what would be the difference between average and weighted average? Anybody? With average, every data point, all data points are created equal, yeah.
With weighted averages, some data points were more significant than others, so they aren't as reduced as others.
Yeah. When it comes to weighted average, you, for whatever reason, have decided to allocate or give greater weight or priority or quantity to particular data points. Classic example of that would be, let's say, we had 5 evaluations in this course. Let's say the first 4 were tests, okay? And let's say the 5th was an exam, right? So you may decide to allocate a weight of 1 to each of the first 4 tests, and then maybe give a weight of 5 to the actual exam, right? So in that sense, you have a total of 6 weights, right? Actually, no, I apologize. That's not true. If we said we were going to allocate, what, 1 to each of the first 4, right? And 5, what did I say?
To the exam.
Sorry?
5 to the exam.
5 to the exam, right? And what do we have there? A 9, right? So then, based on a weighting ratio, each of those first 4 tests has a weight of a 9 in effect, right? Versus 5 ninths, right? Or you could simply say that each of those has a weight of 1, right? The test has a weight of 5, and you can divide everything by 9. We use the formula that they have over here. They're going to list it just for sample of population, but we'll list it for both. So this is going to be pop, sample of pop. Okay, I'm going to let those guys in a second. So they simply write, instead of x bar, they write x bar subscript w for weighted average, weight 1, x1 plus weight 2, x2 plus dot dot dot, weight 3, x lowercase n, all over the sum of the weights. And if we were to write that in sigma notation, if we were to write that in sigma notation, we would have, so just one second please. We would have sum of w I x I. I think we could do it nicer. I think we could just, no, that's fine.
I equals 1.
Yep, all the way up to lowercase n. And we will just divide by, no, we have to have the sum of the weights, right? Okay. So, the only thing is it would be, I think we could put that all in the numerator, couldn't we? Does that make sense? A nice way of thinking about it is, if every data point was what it was, then you just have x1 plus x2 plus x3, but let's say you decide to let x1 be a couple of x1s, right? It's like you have, if w1 is 2, that means you have x1 plus x1, right? If w2 is 1, then you have only 1 x2. If, this isn't good, what should this say? There should be a plus here. And there should be a plus here. You know, if you put a weighting of 10 for data point 3, that's like you have 10 x3s and so on and so forth, right? But then at the end, you can't just divide by lowercase n, because it's not as if you just have n data points. You have w1 plus w2 plus w3 plus dot 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 plus wn data points, right? Because those are the multipliers, or the multiples. Sorry. Those are the multipliers of the quantity of each of those data points, right? So those effectively become the total number of data points. There are different ways you can think about it. Okay, somebody want to go ahead while I let these guys in and use the exact same formula, but write it with the mu notation for weighted average of population over here. Same math. Okay, Kate, are you ready? Your job starts now. First contestant. No, up. Back. Unless you want to stay out. Is that, are those your cards? Yeah. Okay. Ahmad, okay, is the first name, got it? Okay, you're good? Okay, next lady. What do we have? One at a time. That's the video. Rajesh is next. Move it, Rajesh. Quickly. Set yourself up fast. Rajesh, fast. Okay, next. No, we'll get your pen. Yeah. Eric? Yeah. No, it's okay. Move it. You got it? Michael. Michael is next. Guys, newcomers, when I come in here, I want you seated in. We have the full. Yeah. Okay. And just so we're clear, if this represents the universe of data points or the population of data points, when we talk about lowercase n, we talk about that. Right? Is that clear? N is population. Lowercase n is sample of population. Okay? We got that done.
That's one sort.
Next. We have only one other definition to discuss for this section, and then we're going to move on to the next section because this is so easy. And the next one has to do with average. And do they do it for weighted as well? No, but we can do it. Let's say data is grouped and you want to get an idea of average. Now, you can't know the exact average for the population, but you can get an idea of it. So can I erase over here? Let's do mean for group and it's going to be an estimate. In other words, let's say you were given information in like a bar graph, right? Let's say the first part of your bar graph said, okay, let's say your bar graph broke things up into intervals like this.
So that's histogram.
Sorry, histogram. That's why you guys were writing that test and not me.
This is histogram.
Yeah, it's histogram. He's right. Because they're connected, which means it's continuous. Okay. Let's say this is 10. Let's say this is 20. So, if you take a look at this thing, it's telling you that the first bar, it's telling you that there are 10 data points at a value. There are 10 data points at a value of between 0 and 10.
Yeah.
They might all be 5, they might all be 7, one might be 1, one might be 2, one might be 3, a few might be 4, right? You don't know how the data actually behaves within this bar, right? They could all be 10s if you decide to include, I probably wouldn't include the 10. They could all be 9.9999s, right? They could all be 12s, sorry, they could all be 2s. Right? They could all be 0s. You don't know. So, if, unfortunately, you are in a situation where you don't have that data split apart, you're given that data like this clumped up or grouped together, and you are asked to give the mean or the average of all of the population or the sample of all the data you have, whether it be a sample or population. What statisticians say is, okay, well the best you can do is this. Grab the midpoint of each. So what's the midpoint here?
5.
And the midpoint here?
Just you have to sketch a frequency polygon graph.
Pretty much. What they're saying is, okay, use the midpoint. Assume that there are 10 5s in here, and that there are there are 10 5s, and that there are 5 15s, and that there are 20 25s. Okay? Assume that, basically take the total quantity of data points in a bar, and assume that they are all at the midpoint. Does that make sense? There's no spread. You assume no spread within the bar. Like you said, turn it into a polygon. Now, is that true? You have no way of knowing if that's true. In fact, the likelihood is that it's not true, because there's so many other ways that data can be spread apart. So the best you can say is that that is an average. So if we were to do that for population, we would say, now I don't know how they indicate it. Do they use a funny notation for the mu in this case? They still just call it mu. I guess we'll call it mu. Let's call it mu, maybe subscript G for grouped. Does that make sense? And notice we're going to put a dot there because no, there's no need to put a subscript. Why is there no need to put a subscript if you put a dot there? Because we are saying that the stuff we're going to put here, which is based on that method, is an approximation of the actual population average. So we don't need a subscript. So they are right. So how are we going to do this? Well, you could say you have a frequency, let's say. F is going to be frequency. In this case, it's 10 for the of the first data point. And the first data point is going to be the midpoint of the first bar plus the frequency, plus the frequency of the second data point times the midpoint of the second bar plus dot 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 plus frequency of last data point of the population, midpoint. And then, of course, you've got to divide by the total number of data points, which is the sum of the frequencies, which is F1 plus F2 plus dot 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 plus F capital N. And if I was to rewrite that in sigma notation, we would have sum of, from I equals 1 to capital N, Fi, Mi, all over sum of I equals 1 to capital M of Fi. Now, this kind of sucks, but this will be for sample. We will have X bar approximately equals, anybody want to do this one? Okay. Lowercase n, we are going to have frequency I, X, I, all the way. Yeah. All the way to lowercase n of Fi, right? So the only difference between these two, as I can see it, is the capital N's are reduced to lowercase n's. Yeah?
So in the book, they just put under the sigma I, they don't say I equals 1.
Okay. That's a short. That's a short.
Acceptable?
It is, and we'll talk about that when we talk about sigma notation in isolation. Okay, when we talk about sigma notation, we'll probably do that today as well. Yeah. In fact, you'll sometimes very often just see a sigma with an I underneath it with nothing above it either.
Yeah, they put nothing above it.
There's an assumption there. Like you guys know that when I write this, there's a number implied here. What's the number implied right there? Right? And the reason why we don't write it is because of all of the roots that we tend to take, the square root is the one that we take most frequently. So for convenience, we say we can drop it. It's just less work. Well, similarly with sigma notation, you know, but when it comes to something like this, we keep the 3. You're not a mind reader. With sigma notation, you typically start at a value of 1 and you go up to the total amount of stuff. Sometimes you might start at, let's say, 6 and finish at, I don't know, 3 less than the total. But since you most typically start at a value of 1 and finish at the total, they eventually said, okay, well, we're going to start to understand that that just means that. Okay, that those are the same, not by definition, that they're equal to each other, because that way you can save time and space and so on and so forth. But we can talk about that again. Okay. If you were to do this for weighted average, you don't need me to do it for you. I think we all know what you would do. If you take a look at this over here, you have weight 1, weight 2, and so on and so forth. Then over here, you have a weight 1, weight 2, and so on and so forth. Except, what would you divide by? Would you just divide by the sum of the weights?
No, weights and frequency.
Yeah, you'd have to divide by W1F1 plus W2F2 plus W3F3. Do you guys need me to write that for you? Or are you guys cool with that? Ken, you know what I'm saying?
What is?
If you were to do estimate mean, this is estimate mean for grouped data. If you were to do estimated weighted mean or weighted average for grouped data, then you would have W1 here in front of this, a W2 in front of that, a Wn in front of that. And when you divide, you wouldn't just divide by F1 plus F2 plus Fn, you divide by
W1.
F1 plus W2 F2 plus W3 F3 and so on and so forth.
Oh.
Right?
Yeah.
That makes sense? Save me some space. Okay, so we can go further into theory because that's not a hell of a lot of theory. Go a little bit further so we build a bit more context. Because now when you get to page 137, we've talked about central tendency. Now we're doing one variable statistics. Now we talk about deviation or variation off of that central tendency. You know, a good example would be two different runners that run a race. Let's say the first runner runs the race all over the place. Let's say sometimes she's super fast, sometimes she's super slow. She's very unpredictable, not because of extraneous factors like, let's say, she has the flu and so on and so forth, but that's just internal factors in terms of the way she performs. But let's say her average running time is 11 seconds for 100 meters.
Oh, that's slow.
Now, then let's say, is that slow?
Yeah, I think it's 10. It's decent.
Isn't 10 like close to the world record? 10 meters like close to the world record.
It's pretty fast.
Yeah, so what are we talking about?
11
11 is not horrendous.
yeah.
Okay, whatever. 2 seconds and that's it. Okay.
Me is zero.
Whereas you have another. Wait. What do you? No. You're way too late. Find out from someone else. Whereas you have another runner who ran. How many races did I say? 2. 2?
Yeah. Is it?
You have one person. Let's say she runs 100 races. Okay? She tends to, her average race time is, let's say, 11 seconds. And you find a huge spread. You have a lot of times that are low. And you have a lot of times that are high. Not bad.
Low spread.
High speed.
Spread.
You're a loser, Mr. Segev.
Yes, sir.
Can. Really? Get out.
Ken, really? That's what Milad would say. Let's say this is one variable statistic, so there's no x-axis, there's no dependent versus independent. There's only a vertical axis here, if you think about it. Here we have, I think, a total of 12 data points that I drew over here. And I think I drew 12 over here. That was the intent anyways. Let's say analogous to the woman we were speaking about with the running times. Let's say half of the time she's super slow. Half of the time she's super fast. And it turns out that they are perfectly offsetting in a way that balances to an average of mu or x bar. What would be the difference of mu or x bar?
If you're looking at all her races, it's mu. If you're just taking a sample, it's x.
Agreed? What he said there? Here's another woman who, when you average, let's say 12 of her races, whether or not that's all races she's run or a sample, I'm not sure. But they fit a lot tighter around that average. Notice, we have the same average in both cases, right? If you were a coach, want to talk a bit about who you would want on your team, why? There might not be one answer for this. Yeah.
I think I will have that high spread because if I want her to make a record or get a medal, she will be able to do that. But
maybe not all the time, but once or twice. Okay, that's one interesting way. Okay, do you guys follow what he said there? That's interesting. No, but he doesn't care. He's saying, I don't care. If she has some flops, I just want her to be like super fast once in her life, and that's good enough.
You take
Why so late?
I was at the doctor.
Okay, come on in.
I don't know if you want to sit.
I trust you.
Okay.
But the thing is, it's a one-time race, so you need to like. It's only, she's not only, like, they're not gonna let her do like 5 times of 100.
When you say they, this is totally hypothetical. Maybe in this particular thing she runs 300 times a year.
No, I know, but the times that it counts, like in an official match, is only one time. Like,
what?
You usually get up to 3
You guys are, you're making up, you're adding on to the story. Okay, we're making a hypothetical story. In the hypothetical story I created, I didn't tell you how many times she runs. So if there are quote unquote 300 official races a year, that's not unreasonable what he said. If you're going to say that there's only one official race a year, then I agree with you that what he said is nonsense. But I didn't say that there's only, let's say there are 300 Olympics a year, in this fairy tale land. Okay? So we need some basis for, yeah.
I was saying it might be better to choose the girl who has very varying degrees because the first.
So far we have one person for this, and now we have another person for this.
Because her low speed results are not in accordance with her capabilities, which means that
may not be,
which means that you can sort of extrapolate that they may have resulted from extraneous circumstances.
So this is a glass half full or a glass half empty kind of a guy. Is he the glass is half full or half empty?
Half full.
What?
It's half empty.
No. He's a glass half full type of guy. He says, this is who she really is. This isn't who she really is.
no, reverse.
Sorry, yeah, because these are times, right? So this is fast. This is slow. saying this is who she really, really is. She tends to run. I mean, we really know. I believe. Alexei believes that this is representative of what she's capable of. And he's like, this is some stuff that is. He's not going to call them outliers because they're real, but he's going to say, I think I know why I can improve on these and bring them down here. Whereas he feels that this person is very consistent. This person has basically done what they can do. They've maxed out their potential. They are consistent. They're pushing themselves. That's how he's interpreting the data. Maybe you have a glass half empty type of a person that would take his argument and flip it and say, you know what, in my opinion, these are fluky. They're not really representative of what she's capable of. I know for a fact that she's really this. So I'm going to go with that person. Yeah.
So I'm going to say that the girl with the highest spread has flaws. Like, she's not always on top of her work. So I'm seeing the half empty of the flaw. I'm saying that...
Figures me loud would be that guy. I'm playing it.
So I'm saying that low spread would be better because she's inconsistent.
She's a known entity. She's reliable. You know what you're going to get. Right?
And you can improve her. But when you improve the other one, you don't know what you're going to get because half of the time she's getting bad results.
So then my next question to you guys would be, you've heard two people choose one person choose the other. You've heard three different explanations for the choices. Is there a right or wrong answer? That is to say, do any of you feel that one of them had the most compelling answer or not? You want to expand on that? Yes.
I guess, like, if you look at Milad and Alex's arguments, they kind of like cancel each other out because it depends on which way you look at it. If you have, if you're looking at that the slow speed doesn't represent her, or the fast speed doesn't represent her, but the low spread, she's maxed out or she's not maxed out. So
which is it?
Exactly. So they kind of cancel out. But if you look at Ken's argument that whenever she runs fast, she's going to win me medals, right? That might not be also a guarantee because then you're looking at other competitors in that race.
That's interesting too.
Right? So even though if she runs the fastest time, like let's say 10 seconds, there might be someone who ran like 9 seconds and beat her.
True, although that is hard for us to
say from this data.
You're right. But I think what I'm trying to drive you towards, which even in your last comment is kind of suggestive of, is that the answer is that at this stage of the game, there is no best answer. Based on everything that you know in this little fairy tale that I set up, you've all given equally legitimate answers. And if what we call if we deem the correct answer to be the answer that is most reflective of the better runner, we have to define what better is. It's an objective, and we need more information. Okay? In order for Alexei to suggest, in order for Alexei to come up with a conclusion that he had, which is, I think that this is who she is versus this, he would have to go and do more investigation of data points. Right? Analyze her running technique. Give him some reason to feel confident in his assessment that these really, in effect, should have a higher weight than these, if you will. Okay? Having said that, one thing that we can say for sure is that all things being equal, although these two scenarios have the same central tendency, in terms of average in this case, they clearly do not have the same spread about that central tendency. That is to say, these two scenarios are different from each other. We all agree with that, right? They're very different scenarios. If I wasn't talking about a runner, but I was talking about a car manufacturer, and let's say this represented quality. So this is high quality, low quality. Let's say this is average quality, produced by that particular auto manufacturing plant. Let's say the company stipulated that the minimum quality standard that they want across the board for any of their cars would be at a height of this. Then which one do you go with?
Obviously the low spread.
Obviously this one, because you say, well, both of them on average exceed the minimum expectation of the company, but I can count on this guy. But yeah, sometimes this guy is making engines that are good for, let's say, a Ferrari, but I'm selling Hyundais. I'm not guaranteeing that to my customer. They're only paying $30,000, $35,000 for a car. That's nice, but this is a problem to me. This is not acceptable. This is wonderful, but I'm not getting any points for this. This causes my business trouble. Here on their worst day, they're still exceeding my guaranteed minimum, right? So context is huge. But I think we can all agree that based on this little discussion, knowing the actual spread of data about the average or central tendency of the data, it doesn't necessarily have to be average, but knowing the degree of spread of data about the central tendency is useful information. Or it could be useful information. Can we agree on that? That might be useful to know. Okay, so at least we've defined, or at least we all agree on the fact that knowing the spread of data around the central tendency of the data is valuable, or at least can have value. It might be something that you want to check out. Now we come to the situation of, well, how are we going to define? How are we going to define it? How are we going to define spread? Well, again, much like central tendency describes behavior for all of the data with one number, whether it be mean, median, or mode, when it comes to spread of data, we're going to end up quoting a number, a single number. And what we're going to do is we're going to do it relative to average. And the first thing that we have to do is we have to define what's called deviation. We have to define the spread of a data point, any data point relative to the average. So, for example, the distance from this data point to the average would be, let's say, xi minus mu. Or you could call it, for a sample, xi minus x bar. Agreed? This is the average, and this is any data point. Okay, agreed? That's how far a data point is from the average. Now here's the thing. For data points above mu, those data points are going to be positive. Agreed?
Yeah.
And for data points below mu, those are going to be negative. Let's say this is this was 11 seconds, right?
Yeah.
Let's say this is 12. 12 minus 11 is 1. So you have a deviation of 1 second there. Whereas if you had a data point here which was 10 seconds, 10 minus 11 is negative 1. So this is going to be defined as deviation. So it's the value of the data point minus the average, and it's defined the same way for population or for sample population. The only difference is the notation, because for population average is mu, for sample of population it's x bar. And now we've got to figure out a way to take that definition, which is on a per data point basis, and turn it into a number that is reflective of all the data. So one of the things you might be tempted to do is to define something called the overall deviation. Let's say we come up with a term and say overall deviation of data. And we're going to make this up, because it doesn't exist actually, but we're going to make it up. And we're going to say, well, just add up all of the deviations. By the way, does the book use a symbol for deviation? I don't think they do.
Yeah.
For population.
No, they do not.
Yeah.
They do.
What's the symbol?
It's like, oh,
No, you're jumping the gun. You're going to standard deviation. You're jumping the gun. That's not that yet.
so there's no sugar.
There it is, but it's off the top of my head. I don't remember what it is. But the bottom line is that it would be equal to, let's say we'll do it for pop. It'll work out the same the other way. So this will be equal to sum of I for 1 to n of x I minus the average, correct? Which is going to be mu. Agreed? You guys agree with that? That makes sense? More? Okay. These two, does that make sense? It's a grade 9 math student I had last year. Just to be fair. Do you think that would be pretty good? That actually,
No.
that would be brilliant.
Wow.
If I did a 75-minute class, totally serious, and told you guys a whole bunch of crap and fooled you for 75. But you guys are smart, you'd figure it out.
Yeah.
I've
If
learned
I made it really convoluted.
Sir, I know
So
that.
you should do an experiment. Imagine doing it right now.
So one day,
Okay.
one day.
So, who understands what this means? Who understands what that means?
That's the overall that we.
That means,
The sum of all the deviations.
yeah, it means that you do x1 minus mu plus x2 minus mu plus dot 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 plus x3.
Why is it mu? Isn't it mu?
No. What does mu represent? The average of all of the data.
So mean average.
That's a constant.
It's a mean average, right?
What?
Mean means average. You just said when by saying that's the mean average, that's not saying it's the average
It's
average.
the mean, right?
It's like saying it's the blue
No, it's
blue.
not the mean. You're not dividing it by anything.
No, it is the mean.
It is the mean.
Mu is the mean.
Mu is mean.
Yeah, mu is
Mu is mean for population. X bar is mean for sample population.
Okay.
So why not do that? Why not simply measure the distance of each of the data points to the actual average, positive or negative, add all of those together and report that value as the overall deviation, if you will, of all of the data. That's not bad, right? No, Christian, it's not going to answer.
But
Wait, I didn't.
Well, I said I defined deviation for a single data point relative to the average of the data, whether it be a sample of population. If I want to now try and describe an overall behavior of deviation of all of the data as kind of in a general sense, relative to the average, why not simply measure those deviations of each of those data points to the average and add them all together?
You're gonna get a massive number.
no,
You're going to get a massive number.
some numbers will cancel out. And
Some numbers will cancel out.
And then you will not.
Oh,
have
you'll get 0.
You'll get 0.
But there's still some
If it is zero.
You won't get 0.
If you
You will get 0.
If you get zero, and then you will not understand what is happening.
You will get 0 and then you won't understand what is happening.
like
You guys are laughing like
So are you saying the absolute value
That's
or
actually the
the
best answer. Anyways, go on.
You won't get 0.
You won't get 0.
You will get zero.
And that's why we can settle this debate by now taking 2 seconds to learn a little bit of rules of sigma notation. Okay? And kind of take this away for a second.
Sir, this is a question. Do you mean the
May I continue for a second?
Yes,
No?
sir.
Okay. We have to do a few asides here. We have to do some rules of sigma notation.
Is that it?
No, I'm not finished.
No, I'm explaining to Tony what your question was.
Okay, first things first.
When you're ready, you can go into it.
Be nice and close it. Can we, does that seem true?
Yes.
That if you have the sum of A and B sub I, each sub I, subject to 1 sigma, you can break them into 2. We can prove it quite easily by simply taking this
Yeah.
and saying that that's going to be equal to AI plus, no, A1 plus A2 plus dot 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 plus A n plus B1 plus B. Oh, no, I'm starting at the end. A1 plus B1 plus A2 plus B2 plus dot 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 plus an plus bn. And of course, the order of arithmetic, sorry, the order of addition, subtraction is irrelevant, or addition is irrelevant. So we could say that that's the same as that. And then we say equals right side. You know what I should have done? I should have just done this. I should have said ls left side equals that, which equals right side. Okay, so that's one thing that we can do. Agreed? So if that's true, then I can rewrite this as equals this. Like that, right? And then you could have think of this as plus negative that, right? So then you can just have plus negative that, which is the same thing as just negative. Alexei is watching me very closely. I don't think. I turned up doing my work and I looked and he gave me this look. It's like I'm watching you. I'm watching you, you charlatan. Okay.
You asked my question.
Okay, so next. So, I don't know what that was. But anyhow, moving right on. Anything sub I is a variable because obviously when the I value changes, the x value changes. So anything sub I, this is important for you guys to remember and understand. Anytime you see a sub I or a sub whatever letter is under the sigma in sigma notation, that can change because x1 may be different than x2, may be different than x3, and so on and so forth. But if you see a quantity such as this with no sub I, or whatever that letter happens to be, then it's a constant from the perspective of that sigma. It's not going to change. So we are going to take advantage of that, and we're going to do another aside. And the aside I'm going to write here is to say that I1 to n of a, okay, where this is a constant, okay, is the same thing as, well, you start out with I equaling 1, and everything in here is going to be what it is.
Hey.
And then you let I equal 2, and you add to that what's in here, but what's in here?
A.
And then you let I equal 3, and you add to that what's in here and what's in here.
So it is
Good job, Ken.
Eli, you're such a jerk.
Okay,
Okay, you have n of them. So the sum of a constant starting at 1 to n can simply be written as the number of times you do the addition times whatever that constant is. If this was I is equal to 1 to n minus 1, then you wouldn't have n times a, you'd have n minus 1 times a, right? Because you wouldn't be doing the addition n times, you would be doing it n minus 1 times. Or conversely, if you started at I equals 2 and you went to n, this would also be n minus 1 times a because you didn't go through the addition 1, 2, 3, 4, 5, 6, plus, n times, right? So it's the number of times you go through, which is really from here to here, times whatever the constant is. Do you guys agree with that?
Yeah.
Well, if that's the case, then we can now take this whole thing, slide over here.
Such a mess.
You guys are used to it. And we can replace this term on the right with n mu. Agreed?
So I'm missing an xi over there.
Yeah. And in order for us to come to a conclusion, we just have to ask ourselves, Alexi, again, what was the definition of average? Whether it's population or sample population, it's simply
The sum of all the terms divided by the amount of terms.
excellent. The sum of all of the terms divided by the number of terms. So this is going to be the sum of all of the terms.
Divided.
So those xi.
Sorry? Yeah. The sum of all.
Oh, yeah.
The sum of all of the terms which is going to be that, divided by the number of turns.
You cancel it out.
Oh, it is equal to 0.
So, in fact, Ken is right. And Alexei said that too, right? I can't remember, you said a lot of things, I can't remember. But I remember him saying, I remember Ken saying, it's going to come out to 0 and then you won't know anything, something like that. And I like that.
Yes, thank you.
In other words, if you utilize that method, all of the information is buried. It's vanished. It was combined in a way that's always going to give you the same result, regardless of the unique deviations of each of those data points from the average.
That's what they don't.
So, yeah.
The reason I said it's a massive number is that document the absolute value of the deviation.
That's what I thought too.
So, we'll talk about that in a second. So, are you guys clear on that? So then, is there any relevance in defining overall deviation of data as simply the sum of the deviations? No. Doesn't do anything for you. So then,
It must be 0.
Alexei says, one thing you could do is simply do this. Put one of these here, and put one of those there. Agreed?
Yeah.
What does that mean? It means absolute value. What does absolute value mean again? It means that any time you get a negative deviation, it becomes positive. So you cannot have that cancellation offset, in which case your deviation will always be 0 or greater. But statisticians tended not to use it. And the reason why they tended not to use it is because we're eventually going to start to discuss continuous data. And when we discuss continuous data, we get into rate of change, calculus, differentiation, and when it comes to differentiating an absolute value function, you would have to make it piecewise in order to do so. You'd have to break it up into 2 parts. So although I agree with you, Alexei, that putting those bars over there would now eliminate this problem, whereby you would maintain a difference between various situations, they didn't go with it.
We can actually do much with it.
They didn't go with it.
Square root the square.
You could square root the square.
Which is similar back below.
You could square root the square. Anybody hear that?
Yes.
So he's saying, take each of the deviations and square them. As you know, when you raise any value, going back to grade 7, 6, 5, whatever, I don't know. When you raise any value to, you take a real number and you raise it to an even exponent, your result is always going to be positive. So that works, right? And so what statisticians elected to do was, yes, they elected to do that. They took the square of the deviation, and then they averaged that. They averaged that. So they squared all of the deviations, which makes them all, as you said. They averaged that. And then they actually defined that as something called variance. You guys are going to have to double check. Okay, and this is going to be for population. And then they said, well, that's cool. You're right, that would give you a very large number. And moreover, in terms of units, it would give you a unit change. So if you were talking about running times and you're dealing with seconds, now if you define things, sorry, I took out the square, no, we'll square root after. So if we're talking about running time, so this is really the, right here, this is variance, this is the average of the squares of the deviations. If your measurement of your data is in centimeters, then your variance is going to be in centimeters squared. If your measurement of your data is in seconds, your variance is going to be in seconds squared, and very often the information is reported as such. But they also went ahead and said, or we can define standard deviation as the square root of that. Let's go like that. What am I doing here? I have no idea what I'm doing here.
Yeah, oh, but it has to be in seconds. So,
Sir, why don't you just put absolute value outside?
Sorry, let me just finish this up. And by the way, this line should carry over, right?
Yeah.
Yeah, it should be
Can I
like
go this? This line needs to go straight across. Gotta go like that. Now, there, if you, by taking the root, you get back the same units as the actual variable. So if your variable is in seconds, your standard deviation is in seconds. What is the symbol that they use for variance for a population? Well, for standard deviation, they use sigma, correct?
Yes.
yeah.
Lowercase sigma.